not just points, but entire equations. And some of our most useful translations or kind of conversions is that every x we know should equal r cosine theta, and every y should be r sine theta. So that's going to be helpful. And then obviously we also remember x squared plus y squared equals r squared. So if it's converting rectangular to polar, so I see a y here, it makes sense to substitute that for r sine of theta, because every y is r sine theta. And when I see an x, let's call it r cosine. So 2r cosine theta plus 5. Now, when we're trying to write a polar equation, remember, polar equations have to begin with r equals. So when I see a couple r values, let's get them isolated, and so, or like on the same side, so we can isolate it. So I have r sine theta. I'm going to subtract 2r cosine theta to the left, and then factor out that r. So I get it, this expression sine theta minus 2 cosine theta is equal to 5. And then we can divide that across. So here is our polar equation. 5 divided by sine of theta minus 2 cosine of theta. Okay. And so, we will know it's a polar function. And I know I said this before, but just to reiterate, a polar function is any polar equation that can be written as r equals. So it doesn't matter how complex the right side is. There's no vertical line test. It's just, can you algebraically express r equals? And so we definitely could. So it's a function. Now, not really a surprise, because this was a function in the xy plane. You would think it would be a function in the polar plane, and it happens to be. And we're going to find some interesting things happen in our polar world. So now let's look at the next equation, x equals negative 6. Well, I know that's a vertical line in the xy world, and I know it's not even a function. It fails the vertical line test everywhere. But if I'm converting it to polars, every x is equal to r cosine theta. And I can solve for r. So r equals negative 6 divided by cosine of theta. Some people like to say negative 6 times secant of theta. Regardless, we've got r by itself. And guess what? It's a polar function. It was an equation that could be expressed in r. So it's kind of interesting that in a xy plane, a vertical line is not a function. But in the world of polars, we can represent it as a function. And that's one of our first advantages of polar equations, is that allows us to represent relationships that previously weren't functions, and that lets us to represent them as functions. Okay, speaking of non-functions, look at C. That's a circle. Maybe you recognize that from geometry. X squared plus y squared equals 36. Our conic section, that's a circle, 0 eccentricity. Or I know that every x squared plus y squared is equal to r squared. And then if I introduce a square, so technically I should have like a plus or minus 6. But if I have a circle of radius 6, going in, I go like this, or if I have a circle of negative 6, it just starts at the opposite end, but still draws out the exact same circle. So you really only just need it once. So I'm just going to choose it's positive, r equals 6. And guess what, folks? That's also a function because it was written as r equals. So again, something that's not a function in the xy plane becomes a function that we can represent in the polar plane. And our last one, x equals 4y squared, in case you want to know what this is. It's a parabola that's open to the right, so it's definitely not a function. But we're going to find out in the world of polars, it will be. Sorry about that, spoiler in case you weren't sure. So every x is equal to r cosine of theta. Every y is equal to r sine of theta. So we're going to square that. And so then what we end up getting is r cosine of theta equals 4r squared sine of theta, or sorry, sine squared theta. Now, when we're graphing this, we are assuming that our radius is positive, aka not 0, I should say. So one thing we can do in the world of polars that we shouldn't do in the world of rectangulars is that we can if you have multiple powers of r, you can divide out the r because our radiuses have to be measurable. So we know we're not worried about dividing by 0. So then that becomes cosine of theta is equal to 4r sine squared theta. And let's get r by itself. So we'll divide the sine and the 4 across, sine squared I should say. So cosine of theta divided by 4 sine squared of theta is equal to r. And there is a polar function that was not a function in the rectangular system. Okay, so now going backwards, our goal is to try to create r cosine thetas, because then we can replace them with an x. Or create r sine thetas, because then we can replace them with a y. Or create r squareds, because then we can replace it with x squared plus y squared. So when I look down here in the bottom, um, like I noticed that 7a has r equals where this is r and a sine. So I'm going to treat them differently. It might be easiest for a just to square both sides. R squared equals 16. After all, this is a circle of radius 4, so I know what it looks like. And if I square both sides, r squared equals 16, I'm like, oh, I know that. That's x squared plus y squared equals 16. So I'm back in my rectangular version of the circle that I already knew was centered at 0, 0 with a radius of 4. So squaring both sides was helpful here. Square both sides. It didn't introduce anything more complicated other than an r squared. I would contrast that with trying to square things on this side. Don't. Because if you try to square things, yeah, you pick up a nice r squared, but now you pick up a 64 sine squared theta, and that doesn't help you at all. So rather than squaring both sides, it might be beneficial to multiply through both sides by r. And so that's sort of like our second technique when we're converting from polars back to rectangular. If I distribute that r, I get the r squared that I desired, but I also get an 8r sine of theta. Well, we know that r squared could be written as x squared plus y squared, and we know that an r sine theta is equal to y. And at this point, I'm okay just leaving it like this. It just says convert. It doesn't say we have to write it in standard form, general form. I mean, this is a circle, so I can't possibly get y by itself in just one equation. Could complete the square to find its center. I know, if you have me first semester, you know how much I love that. Minus 8y is equal to 0. I'm just doing this because it's fun. You don't have to. Plus 16 equals 16. And so then we get x squared plus y minus 4 squared equals 16. So this circle is centered at 0, 4. And its radius is 4. So a little bit more than we have to have done just that. And again, contrasting, it's a function in the polars when it's r equals. Clearly, this is not a function in the rectangular world. Okay, and so let's continue. So let's multiply this denominator across. So we get 6r minus r cosine of theta equals 6. And you might recognize an r cosine theta as an x. Let's use that to our advantage. So 6r minus x is equal to 6. Now, we kind of want to get rid of all of our r's and thetas, but we don't want to undo what we just did by converting one of our cosines to an x. So I'm going to move that x across. So I have 6r is equal to 6 plus x. And I'm going to now square both sides. So that way I don't get the hybrid kind of an x and an r if I didn't isolate it first. So I get 36r squared is equal to 36 plus 12x plus x squared. And then this r squared here can be represented by a quantity x squared plus y squared equals 36 plus 12x plus x squared. Now I distribute the 36, and I'm recognizing I got some quadratic terms here, x squareds and y squareds, but I should probably put like things together. So let's move everything over to the left. So I subtract x squared, and I get 35x squared plus 36y squared. And then when I move the minus 12x over and I move the minus 36 over, I get 0. So I'm going to leave it like this because again, I have to simplify in terms of like completing the square. But please realize this is no longer a circle. If my quadratics are both positive, but one is being stretched more in direction than the other, we know that this actually is an ellipse. But again, we're not graphing it, we're just rewriting it. Ellipse is not a function in xy, yet because it started with r equals, it certainly is. Okay, now you could pause the video and solve D and see if you get it right. Or we can keep watching. So I'm going to multiply this denominator to the left. So I get r plus 2r cosine of theta is equal to 1. And then similar to the last example, this r cosine theta can be an x. So r plus 2x is equal to 1. Isolate that r. So we get 1 minus 2x. So now I'm going to square both sides. So I introduce the r squared. And I get 1. Oh, actually, I can just do that. Sorry about that. We can multiply. So that was 1 minus 2x. So we get 1. I'm squaring both sides. Well, that's okay. I'll square this. Okay, so that's r squared is equal to 1 minus 4x plus 4x squared. And of course, we knew r squared was x squared plus y squared. So again, maybe putting everything over to the left or right doesn't really matter. Let's maybe move everything to the right this time. So 0 equals, if I subtract x squared, I'll get 3x squared. If I subtract y squared minus y squared, and then I still have this plus 1 and a minus 4x. And so again, we're done in terms of our task for this problem. And maybe we recognize this. It's two quadratics with it's a difference. So this is actually a hyperbola, which is not a function in the xy world, yet in the polar world it was. And at the very bottom, if you haven't written this down yet, it's really important to note, right? To be considered a function in the polar system, the equation must be written as r equals. So if you don't write it as r equals, you're not a polar function. And you might be wondering, are there examples of things that aren't polar functions? The answer is yes, but you can think about that or wait for another lesson.